Okay, let's start. So our next speaker is Gal Kronenberg from University of Oxford. And she will talk on independent sets in random subgraphs of the hypercube.
Yeah, I mean, if
Gal, you can start.
Thank you. Okay. So thank you, Liana and Andre, for organizing it twice. So I'm sure it was difficult. Yeah, so I will talk about independent sets. So I will start by talking about independence, counting independent sets in the hypercube, and then I will move to random subgraphs of the hypercube, which will be the main topic here. But before talking about counting independent sets in the hypercube, let's start with a little bit easier setting. Instead of counting them hypercube, let's start by counting them just in bipartite graphs. So hypercube, as you all know, is a bipartite graph, the regular bipartite graph. So let's see what happens when instead of hypercube, we consider the complete bipartite graph. I'll have to say it a lot this talk. KDD, so we have two sides of size D and all the edges in between. And I want to count how many independent sets do I have in this graph. So this is pretty easy because we know that in each side is an independent set, of course. So all of the independent sets, the number of independent sets on each side is 2 to the D. And we cannot have in this graph an independent set which is contained in both, which has parts in both sides, right? Because if I took something from this side, I cannot take anything from the other side because it's complete. We have all the edges in between. So every independent set lies on exactly one side. So we have, by symmetry, we have 2 times 2 to the D, but -1 because we don't want to count the empty set twice. So this is the total number of independent set in this simple graph, KDD. And if okay, so let me add some notation here. So IG will be the total number of independent sets in the graph G. And if we want to write what I wrote before in terms of the number of vertices, n, which is 2D, so I will write it like this. The number of independent sets in KDD is 2 times 2 to the power of n over 2 minus 1. And the reason that I want to write it like this, so it will be easy to compare to other results later. Okay, so let's do now a little bit more complicated example, but still simple. So instead of 1 copy of KDD, I want to take k copies of KDD, and I want to count the number of independent sets here. So this is also pretty easy because in each part, we know that the number of independent sets is this thing, and we have no edges between the different copies of KDD. So we just put it in the power of k, and we have the total number of independent sets in this graph. And once again, I want to write it in terms of the total number of vertices. So this is what I get. The total number of independent sets, it's 2 times 2 to the D minus 1 to the power of n over 2. Okay, so now what happens with more general deregular bipartite graph? There was a conjecture that so it was formally stated by Kahn only in 2001, but already Alon mentioned it, and even before in some weaker form. So the conjecture says that if we want to count the number of independent sets in deregular graphs, here I wrote bipartite because this is the talk about bipartite, but the conjecture was for any deregular graph. Then this example, it's the best thing you can hope for. So this will maximize the total number of independent sets. So the conjecture says that for every deregular bipartite or non-bipartite graph G, the total number of independent sets is at most what we get here. The total number of independent sets in this example, k copies of KDD. So I wrote it in terms of the number of vertices, and this conjecture, so Alon proved the weaker version of this conjecture, and this conjecture was proved by Kahn in 2001 and later by Zhao in 2009 for every graph, not only bipartite. But once again, we focus here on bipartite graphs. So I'll just mention that Kahn's result is really elegant, and I will not have time to show it here, but I really encourage you to read it because it's a very nice using of the entropy method, and it's really elegant. Okay. So we know that we have an upper bound for the total number of independent sets in every irregular bipartite graph, which is this. So now let's move to the hypercube, which is the irregular bipartite graph. So QD is 0, 1 to the D, the D-dimensional hypercube. We know that it's bipartite and it's irregular. And we have the upper bound. So we have the upper bound that we saw before, according to Kahn. So the total number of independent sets in the D-dimensional hypercube will be at most this thing. Okay, but what about the lower bound? So let's see what can we say about the lower bound. So we have two sides on the hypercube. It's a bipartite graph. Each side has 2 to the D-1 vertices. We call the side sometimes even an odd because it's just simpler. So the total number of independent sets in each side will be 2 to the power of the number of vertices. And exactly as we calculated before, so we have 2 times this, and we don't want to count the empty set twice. So we get a lower bound exactly like we did before, which if we write it in terms of the number of vertices, looks like that. So we have an upper and lower bound, and they're pretty, okay, they look similar because in both of them we have the term 2 to the n-2. So here will be 2 to the n-2, and here we have the 2 to the n-2. But here it multiplies by 2, and here it multiplies by 2 to the n/2d. So if n is much larger than d, which is the kind of graphs that we want to think about, then the upper and lower bound are pretty far from each other. And the question that was asked is what is the truth? Okay, so what will be the truth? What is the total number of independent sets? And result that I'll show you according to that I will show you in a second, will show that the truth will be closer to the lower bound and not to the upper bound. So it will not be exactly like the lower bound, but it will have the same order of magnitude like the lower bound. And let me just recall you that how did we get the lower bound? We just counted, we only considered independent sets that are entirely in one side. We didn't allow independent sets to be on both on the even and odd side. And the fact that the truth is closer to the lower bound will hint that actually most independent sets have a majority part only in one side and only a smaller part on the other side. So this is exactly the truth. So let me state the result of Korshunov and Sapozhenko from the 80s. So they showed that the total number of independent sets is almost like the lower bound, except that we have this another constant here of square root of e. So this exactly shows that that we're closer to the lower bound, and they in fact showed something even stronger, that they also considered the structure of these independent sets, and they did show that most of them have the structure that the majority part lies on one side of the hypercube of the bipartite graph, and only small part will be on the other side. Okay, so we have really the structure of it. Do I have time? Yeah, let me just sketch the proof of the lower bound. So the upper bound will be much more involved for this theorem, but the sketch for the lower bound only, so you'll have a taste of what's going on here. So how do I get, so I get you before the proof of the lower bound without the square root of e, which was very simple. So how do we get the square root of e? So if we choose a set of k vertices from one side of our bipartite graph, so how many vertices on the other side will be forbidden now? So at most kd vertices, because each vertex has the neighbors. So if we choose k vertices on one side, at most kd vertices will be forbidden for the other side for an independent set, and therefore how many independent sets will we have that their k side, the small side, will be on the even side, for example. So we need to choose these k vertices, and then we need to choose whatever subset that we want from the other side. We need to be careful not to take the forbidden kd vertices. So this gives us this estimation, which is roughly like this, and summing over all k, we get this is where we get the square root of e here, and the 2 to the d, and the 2 here, it's just because of symmetry. Okay, because we can take the smaller side to be on the even side and then on the odd side. So this is roughly it's almost the proof. We just need to explain why we don't have a lot of double countings here. But this will be roughly the proof of the lower bound, and the upper bound is much more involved. Okay, so this is the result for counting the number of independent sets in the hypercube. And many years later, very recently, Matthew Jenssen and Will Perkins actually improved this result. So they were able to determine this little of one term much more accurately. So you can see again, we have the 2 here, we have the square root of e, we have the 2 to the 2 to the d minus 1, and here we have a much better estimation. And in fact, I wrote 3 dots, but the result is using the tool of cluster expansion, which I'll hopefully have time to talk a little bit later. But the idea is that you can get the estimation is as good as you want. So choose k, and you can just calculate the series here up to whatever accuracy that you need. Okay, so this is basically solves the problem of counting independent sets hypercube. And I'll just mention here another result of Galvin, which hopefully I'll focus on later. In 2011, he was able to generalize the result of Korshunov and Sapozhenko, also for not only for counting in the independent sets, but also for weighted counting. So when we count with weights, so he did this, and also Jenssen and Perkins did. So the result is also generalized this setting, and I'll explain more about the weighted counting later. Okay, so now it's time to move to the random setting. So let's talk about random subgraphs of the hypercube. Okay, so we want to extend what we know about the number of independent sets in the hypercube to random subgraphs. So this will be our setting. So QDP will just be, so we flip a coin on each edge of the hypercube independently with probability P, and this gives us a distribution for a random subgraph of the hypercube. Okay, so this is the object that we're interested in, and we want to ask about the total number of independent sets here in this object. And once again, we have okay, so we have, of course, the obvious lower bound that we had before, where we consider only independent sets that are entirely in the even side, and only dependent sets that are entirely in the odd side, and that's it. So we still have the same lower bound that we had in the very beginning here. We still have this lower bound, and now we want to ask for a better lower bound. Also, in the random case, we will get a lower bound which is similar to the one that Korshunov and Sapozhenko got. So we also have a lower bound here. So you can see that if we take p equals 1, then we get exactly the lower bound that we had before of Korshunov and Sapozhenko. But this is generalized to the random subgraph, setting, and the proof is similar in its spirit from what I showed before. But in this case, we also need to show some concentration, so it's a bit more involved, but it's really the easier part. Let's say the lower bound, the upper bound will be the more complicated case. Oh, and one more thing, we have some bound on P here. So I will also discuss the different values of P later. But of course we need, so here I have with hyperability results. So we also need some concentration. We don't have concentration for every value of P. But let's see a little bit more general results now. Okay, so what happened with the upper bound? So we want to show that this order of magnitude of the lower bound is again the truth of also for the random subgraph of QD. Okay, so the first theorem will be that we take P can be anything starting from log d divided by d to the 1/3. Oh, so I didn't mention, but we want to think about in the hypercube, we want to think about d being very large. So we want to think about asymptotics as d tending to infinity. Okay, so d is very large in our case. So the little o of 1 is little o of 1 with d. So we have p tending to 0, but not too fast. And the expected number of independent set. So the first theorem will be the expected number of independent set in the random subgraph of the hypercube is similar to what I wrote in the lower bound. So we have once again 2 times 2 to the d minus 1, and we have this e to the power of this, and this time the 1 plus little of 1, it's in the expectation and not here like we had before. But in fact, we can do something better. So once again, using some cluster expansion techniques, we are able to understand this little law of 1 term and write something much more accurate. And once more, we can continue writing it and calculate more and more terms using this technique. It's all yeah, not very difficult to calculate, or maybe a little bit annoying. Okay, so we have the first result, and the conclusion of this result will be, for example, so one conclusion will be that if we take p to be large enough, some larger than some constant, then we actually have that the 1 plus little of 1 term is down here and not up in the exponent, which is much more accurate. Okay, so we have that the expected number of independent sets is of this form. Okay, okay, and 2 more results just to give it flavor. So what happens if I want to give with hyperability result? Then once again, I need p to be larger than 2/3 this time, so p is a bit larger, and then I can generalize or I can give the same result as before in terms of with hyperability. So once again, we get the same term here. And the last thing that I will mention, so another result that it will give us is that if p, okay, so now p is even larger, so p is tending to 1, but not too fast, not too close to 1, then we can actually give something much more information. So we actually know that the total number of independent set is normally distributed after the proper normalization that we need, and the convergence is both in distribution and also with moments. So actually the way we prove it, we actually prove we find the moments of the total number of independent sets in our graph. Okay, so if anyone has a question, this is a good time before I continue. And I'll
Gal, if I understood correctly, so you prove results for the expectation for like a bigger range of P for relatively small P, and the with high probability results for P bigger than 2/3, right?
Yes. So okay, there is one main result, and the one main, I didn't state it here because it's not really nice to write it, but the one main result will be the moments. So we find the moments of the total number of independent sets, and moments will be for the best P. Okay, and now you need to see what kind of conclusions you get. So you get the expectations, and then if you want to put the 1 plus little of one term here and not in the exponent, then you need to take some larger P. And then if you want to ask when it converges, then you need to take a bit larger P. And then if you want to really say the distribution is normal, so you need to take P even larger. And yeah, of course you can ask, what is the distribution when P is smaller? It will probably won't be normal all the way down. So usually this type of.
So can you, for example, say that for the lowest P that you deal with, you don't have a concentration? Like, so if P is say 1 over, so, yeah, okay.
Yes. We also have like a non-concentration results. There, I mean, yeah, and also usually this kind of counting. So it won't be normal all the way down, like normally distributed all the way down. At some point, our guess is that at some point it will be log normal and not normal, but we couldn't prove it. When I will talk a little bit about the proof, you will also see why we cannot.
And maybe one more question, like a side. So what is the, can you remind, what is the P for which we know that the largest independent set is the same? So is it 1 over, is it, because.
What do you mean the same?
The same as in the cube without deleting the edges. So until when we, like what P can we take so that the largest independent set is
so I think that the largest independent set will just be taking one side entirely.
Yeah. What it breaks down, it's for some P. If P is really small, then it'll break down.
Okay, yes. So
I'm just wondering where does this happen? Because is it roughly 1 over D or 1 over?
This is a good question. I don't really know. So what I do know is that maybe it's related. I cannot promise, but maybe it's related. That the connectivity threshold in the hypercube is 1 over D.
Okay.
So maybe, I mean, if you ask me to guess, that will be my guess, that maybe this theorem can be improved up to 1 over D. Maybe it will be true up to something close, not really 1 over D, but something close to the connectivity threshold, but definitely not. So
okay.
It will not be true below 1 over D, that's for sure. And hopefully it can be true for something close to it. So the connectivity threshold will be something to think about here.
Great, thanks.
Okay. So let's talk a little bit about the proof technique, just a little bit because I don't have a lot of time already. Okay, so the main thing that I want to say about the proof. So before talking about the proof technique, I want to redefine all of this story about the counting independent sets, but I want to think about it in a little bit different perspective. So I want to think about it from statistical physics perspective because I will need it for my proof. So let's do some definitions. So this kind of model in statistical physics, they call the hardcore model. So basically we have a room with gas inside. So this is the room and we have some particles of gas inside. And we want to understand how they react with each other, how they distribute, how they look like. So we have some gas model, and the only thing that we want, the only constraint that we have is that particles don't overlap. So how do we analyze this model? Like this, it will be very difficult to analyze. So let's make our room like a lattice. Let's discretize it. Okay, and now we want to think about every particle gas being on a vertex of on a vertex in our graph, which is lattice in the picture here, or the hypercube. Okay, so we can have many things. And how do we think about the gas particles not being overlapped? So we just want to say that every two particles don't share an edge. So this is exactly an independent. Okay, so why do we want to think about it like this? Why do we want to think about the hardcore model? The reason is that we will not prove what we proved directly on the random subgraph of the hypergraph. We will not prove it directly on this setting. So we would like to show that it behaves like some other version of the hardcore model, and we will do all the proof in the other version. So the other version is called the positive temperature model. And what is the connection between these two, and what does it mean? So assume that we have a graph, and we want to calculate the expectation of the number of independent sets of a random subgraph of this graph. So after very few calculation, we can get this form, or this sum, to the expected number of to the expectation of the number of independent sets. And if we write P as 1 minus e to the minus beta, only because this is the way that people from statistical physics want to think about it. So let's write it like they do. So we have this sum, and let's add another notation of this sum to be z of g beta. Okay, so beta is a function of P, and it relates to P. Okay, so what did we get here? So we have another definition. We have a sum, but this sum is like sum of weighted things. So if we take beta to be infinity or tend to infinity, so we actually sum. So here we have the sum on every set, all the subset of the vertices. So we don't only count independent sets. So we count all the sets, all the subsets of the vertices. But if beta is tending to infinity, then it will be 0 everywhere, besides of all of those sets that the number of edges are 0. So besides all of the independent sets. So this z of g beta will count the number of independent sets if beta tending to infinity. And if beta is not tending to infinity, then we have some kind of weighted counting depending on the number of edges in our set. So if beta is very, very large, so we will prefer in some sense sets that have only few edges, and sets that has many edges in them will have very, very small weight. Okay, so we are generalizing the idea of independent sets, and we allow to have edges inside, but we give like higher weights to those sets that have only few edges inside. And once again, we can define the hardcore model here, but this time we have some weights in this hardcore model. Okay, so this will be a hardcore model which has a positive temperature. And I should finish, so just let me, so I just wrote here that we have that this time we're allowed to have some edges in between. And the main idea will be that instead of proving things, okay, on our random subgraph of the hypercube, on the expectation of the random subgraph on the hypercube, we'll actually prove it on this model. And then it will give us something on the expectation of this number. And in fact, it will be true for all the moments. So we can define similar models of this positive temperature hardcore model, which will be exactly the moments of what we're looking for. So by analyzing this model, we actually get something on this model. Yeah. And the tools that we're using, as I mentioned before, will be the connection between these two models. And we also use, so this is for people who know it better. So the clusters expansion and the polymer model. So we use it to analyze this model this time with this positive temperature. So this is very similar to ideas used by Matthew Jenssen and Perkins. But we will also need some approximations to show that this cluster. So this cluster expansion is just a way to write this to write the log of the partition function in terms of some series that we want to show that this series converges. So this will be a difficulty to show that it converges, and so we need for this some approximation tools and also some approximation tools for the positive temperature and understanding the methods, of course, the moments, of course. Okay, so I think I'll stop here because I have no time to continue. Yeah, I stopped.
Thanks a lot.
Thank you, Gal. Let's thank Gal for a great talk. I think we have time for maybe 1 or 2 quick questions. So what's can you go back to your tools?
Yes.
So what's the new ideas that you bring in?
So, okay, so yeah, it's a little bit, I just wrote the names of the tools here for in case some of the people are familiar with the methods. It's a bit maybe difficult to give a lot of information in a short talk, but okay, so the idea is that there is this cluster expansion method, which is maybe mysterious for mysterious for people who don't know it. But as I mentioned, it allows us to write this this sum or this weighted sum as a series of some clusters in a different graph. So we use some auxiliary graph. So it will allow us to write it as a sum, and this method, which was used before by other people, okay, says that if we can show that this sum is that this series is converges, then we can say something about the model. But the difficulty is to show that it converges. Okay, and in our case, so we have maybe 2 more layers of difficulty. So the first thing, so if we just wanted to show that it converges, so people did it before us, of course, as I mentioned, Jenssen and Perkins did it before us for the hypercube and not the positive temperature method. So one layer will be to understand how we do it for the positive temperature model. So this is okay. So how to do it for the random subgraph. So one thing is to understand how, instead of working in random subgraphs, we work with this other model, which with the positive temperature. So this will be like a first step. And after we understand how to work with this model, then we have another two layers of complication. One will be how to use this cluster expansion for positive temperature and not for the normal hardcode model, which wasn't done before in the hardcore model. So people did it in different models, but not in the hardcore model. So And this is what I wrote here. So some people did it for different models. For example, in the paper of Taleb and Spinka, but also maybe in more. So this will be one difficulty. And another difficulty is that we don't only want to understand the expectation, we actually want to understand the moments. So in order to understand the moment, we need to not only to see how we do this cluster expansion in positive temperature, but we also need to understand how we do it with moments. And for this, we define a more general model that we need to work with to overcome this complication. So maybe I said something that someone can understand.
Okay, thank you. That's nice. Yeah, I know a little bit about the cluster expansion in the Galvin. So I was just wondering what else do you add towards it? But yeah, I guess.
Okay. So what else we have? So we need to understand how we do it. So in order to do it for the moment, for higher moments, you actually need, so in the cluster, in the hardcore model, you can think about it as sampling one independent set. And for doing it for the moments, you want to sample not one independent set, but several independent sets that somehow interact with each other. So you need to make it a little bit more complicated to understand the higher moments and not only the expectation. And you need the higher moments for the concentration, of course.
I see. Okay, thank you, Gal. Let's thank, I don't think we have time for more questions, but let's thank Gal for great talk, great results.